Welcome to Model Eval, ML Model Eval Session 3. Today, we're going to go through prediction probabilities and thresholds. So today, we're going to talk about how to determine that 1-0 classification based on a model probability. So some models will predict just 1 or 0, but other models, algorithms that we've learned about in the previous class, actually output probabilities. And when we have those probabilities, how do those probabilities get transformed into that 1-0, this is a banana, this is not a banana, this is a cat, this is not a cat output. So we're going to talk about prediction probabilities and thresholds. Just to recap on this, we've talked about that a little bit in the last class. But the reason we're talking about that is because we're going to use that to understand the receiver operator curve and the precision recall curve and area under the curve. So up to this point, we've talked about metrics that just produce a performance metric for a model at one threshold. We're going to look at metrics that evaluate model performance across several thresholds. And then we're going to talk about model calibration kind of on the very end as a way that you can calibrate model probabilities to match the real world, what people would expect as probabilities. So we've got a couple exercises in here, and then we have a little extra breakout notebook for model calibration. So probabilistic models and the ROC curves. First, we're going to talk about this. Probability in the context of machine learning represents the likelihood that an event would occur. So when we have a model that outputs a probability of 0.8, it's a measure of how likely it is that that event will occur. And this is a numerical measure. It's from 0 to 1, where 0 represents the impossibility of the event. The event is very likely to not occur, and 1 represents the certainty of the event, the likelihood, very certain that this event will very likely occur. So probabilities close to 1 imply a higher likelihood of the event occurring, while probabilities close to 0 suggest a lower likelihood of that event occurring. And this is sometimes interpreted as sort of confidence. What's the confidence that the model has in this outcome happening? These probabilities are sometimes interpreted that way. So for example, if we toss a fair coin and the probability of it landing heads up is 0.5, there are 2 equally likely outcomes. It's just as equally likely that it would be heads as it is that it would be tails if it's a fair coin. This is similar to our binary classification problems, where the output by the model might indicate the likelihood of if it's 0.5, it's just as likely to belong to class 1 as it is to belong to class 0. So this is the degree of belief or our confidence that this event will occur. When I say event, we're talking about whatever the prediction we're trying to make is in question. So the probability that there is a cat in the photo, the probability that it is a banana, the probability that it is fraud. In machine learning, our algorithms, our models that we learned about in the last class, they output probabilities depending on the specific algorithm that's implemented. But as we looked at logistic regression, and that gives us a probability input belonging to a particular class. We know that it does that through the sigmoid function that takes our negative z and squishes it. So we looked at that last class, how the sigmoid function constrains that output between 0 and 1, and we interpret that as a probability. And we looked at decision trees and random forests, and random forests serve a probability from multiple decision trees. So we take a voting structure and we take a count of the votes, and then we could convert that count of the votes compared to the whole. So if 80% of the trees made a particular recommendation, a particular decision, then we interpret that as 0.8 probability. So these algorithms are ones that we looked at as a reminder that output probabilities that represent the likelihood of belonging to a positive class. Knowing that we have probabilities, knowing that we have not just, yes, this is this class, but we have almost a degree of confidence or a degree of belief that it is a particular class, we can employ something called a threshold. So in the context of machine learning and our classification problems, this is classification, not regression, we can employ a threshold which says when the confidence or when the probability or when the degree of belief is above a particular amount, I believe it's going to be this class. And when it's below a particular amount, I believe it's going to be the other class. So we can use this threshold to make a decision about which class the data point belongs to based on the probability of the output. So if we have, I thought I had a good picture in here, but I don't see one now. So if we have output probabilities, we have 0.1, we have 0.5, and we have 0.9. We could say for 0.5 is our threshold. So every output that has a probability greater than 0.5 is 1, and every output that has a probability less than 0.5 is 0. But we don't have to put it at 0.5. We could put it at 0.8. And this would be 1. And this would be 0. What do you guys think would happen to precision if we put the threshold at 0.8 relative to 0.5, just generally speaking? We don't have a data set here, but generally speaking, how do you think that would influence precision?
So just to make sure I got the question right, you're saying if we set it to 0.8 instead of 0.5, wouldn't that make it more accurate, so give it more precision?
If we set it to 0.8 instead of 0.5, we're only going to predict 1 on probabilities that are on records that we're highly confident on. So only when the model believes it's very, 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 very likely to be a 1, then we're going to say 1. And then for everything else, we're going to say 0. So when we say it's 1, our confidence and degree of belief that it's a 1 is very, very strong. So if we move 0.5 to 0.8, you're exactly correct. It increases the precision. It should, generally speaking, it should increase the precision. However, what's going to happen to the recall?
It's going to have a lower positive rate.
Exactly. Yep. Recall is going to go down because the number of times that we are actually saying, yep, it's a 1 is much smaller. So there's going to be a larger realm of instances that should have been classified as 1 that we missed. So our recall is going to go down. So precision will go up, recall will go down. So how this impacts your accuracy, it actually may not change your accuracy at all, or it may make your accuracy go up, it may make your accuracy go down. It's probably going to actually make your accuracy go down, but I don't know if that's a general rule. We could write a little program and tweak with it. And actually, maybe I might have that for one of the breakout exercises. So we'll do that in, I think I have 3 more slides. If we don't cover that in these 3 slides, then we'll come back to the whiteboard and do this. So how thresholds work. In binary classification models, that output probabilities, we apply this threshold to determine the predicted class. So if we say it's 0.5, then everything above that threshold belongs to class 1, and everything below it belongs to class 2. If we say it's 0.8, everything above it is 1, everything below that is 0. So here we have an example. We have a logistic regression model that predicts whether an email is spam or not spam. So if the model outputs a probability of 0.7 per particular email, and the threshold is 0.5, 0.7 is greater than 0.5, so we do classify it as spam. However, if we set the threshold to 0.8, so let me see if I can just draw this. We have a pred. We predicted, sorry, that's terrible, 0.7. If our threshold is, we have 2 situations. We have when our threshold is 0.5 and when our threshold, I should call this prob. So instead of pred, because I'm going to call pred at the end here. So we have a probability, prob, of 0.7. So, and when our threshold is 0.5, we say 0.7 is greater than 0.5. So the output is 1. And when it's 0.8, we say that 0.7 is less than 0.5, or 0.8, sorry. 0.5 is, 0.7 is less than 0.8, so the output is 0. So I just want to emphasize here that we did not change the model. We didn't change our model at all. We have the same model outputting the same probability, and we're getting different predictions. This is our prediction that we're serving at the end of the day. These for the same record, red. If this is trying to predict an instance of spam, in this case. So same model, same record. All we did is change the threshold, and it changed the output that we're actually predicting. So when we go in, when we evaluate accuracy, we have to look and see, for this record, was it actually 1 or was it 0? So let's say it was 1, was our true. In reality, our ground truth, our true was 1. This one would have been corrected, and this one would have been incorrect from an accuracy standpoint. So same model. We didn't change the model at all. All we did was we changed this threshold value, and it changes the outputs and the performance, the evaluation of our model. So thresholds are a model parameter. I don't know if I want to call them maybe a hyperparameter, but they're an adjustable parameter that can be tuned to really control the trade-off between precision and recall. So by varying this threshold, we can prioritize one type of error over another type of error to meet whatever our requirements are. So let's whiteboard here for just a second, and then we'll open up this breakout exercise. I'm going to go back to that slide we were on where I drew the line here. So let me see if I can pull this whiteboard over. You guys see that? Okay. Let's make a data set here. And say we have, okay, so we want Y pred, y prob, and we want y true. And then we're gonna look at, we're gonna make another table and we're gonna see how, we're gonna make another table over here that is threshold. Okay. Did it go too far? No. Okay. Threshold, accuracy, precision, and recall. Okay, let's look at this, and let's set something ridiculous like 0.1, and then let's do point. I don't know how many of these we want to do. Let's just do 0.5 and then 0.9. Let's just be extreme there. Okay, do those three for now. So here's our data set here. And these are our metrics we're gonna track. We're gonna see how these change. So if our, let's just 0.1, 0.2, 0.3, 0.4, 0.4, 0.5, 0.8, 0.8, and 0.9. Okay. And let's say y true. 1, 2, 3, 4, 5, 6, 7, 8, 9. Let's make life easy on us. Let's put a 7 in here, actually. 8 and 9. Okay. We have 10. Should be easy to calculate. So let's say y true. This was 0. We're going to say this one was like confidently incorrect. Another fairly confident incorrect one. This one was 0. This one was 1. 1 confidently incorrect here again. 0. 1. 1. Okay. Okay, so let's look at our threshold of 0.5. So we're going to do a y pred column that we're going to change each time. So when we're looking at our threshold and we set threshold equal to 0.5, that means that we're going to draw a dotted line here, and everything greater than this is 1, and everything less than this is 0 from a y pred. So we're going to convert these probabilities. What we're doing is we're converting these probabilities. So we're in 0, 0, 0, 0, 0, 1, 1, 1, 1, 1. And now we can calculate our accuracy. What's the accuracy? If we predicted 0, let's do this. We predicted 0, it was actually 0, so we were correct, We predicted 0 is actually 1, so we're incorrect. Predicted 0 was 0, we were correct. These match. Oh. Incorrect, incorrect, correct, correct. What's the accuracy there?
Is the accuracy 55% or 60%? It's a little above half.
Yep, 1, 2, 3, 4, 5, 6. Yep, 60%, you got it. So we got 6 out of 10, which equals 60%. Does anybody remember the formula for precision?
True positives over true positives plus false positives.
Excellent. So what is the precision here? Let's see, which of these are true positives?
Or is it 3/5?
5. Yes, true positive. We predicted 1, it was actually 1. We predicted 1, it was actually 1. So that's 2. So TP, 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 predicted over false positives. So this is, what did you say, 3/5?
Yeah.
Yep. So our false positives are when we predicted 1, false positive, but it was actually 0. So those are our false positives. So 3/5, which is going to be 60%. And what's our, anybody remember the formula for recall?
TP over TP plus FN.
So what's a false negative? Or which of these are false negatives?
Two false negatives.
Yep. So this one's a false negative. This one's a false negative. We predicted 0, but it should have been 1. Predicted 0, but it should have been 1. Remember, we don't care about when we predicted 0 and it was actually 0. So we have 3 true positives and then 2 false negatives. So it's 3/5, so 60%. Excellent. Let's change our threshold. Great. So we got some metrics there when our threshold is 0.5. Let's change our threshold and let's put it at 0.1 just to see how this changes our outcome. So we're gonna, sorry about that. This whiteboard, I need to lock this in place apparently. I don't know. Okay, so let's change our threshold here, and we're gonna put this at 0.1, just to be extreme. I don't know that there's a good reason to actually do that. So everything less than 0.1 is 0, and everything greater than 0.1 is 1. So from a pred perspective, here we predicted 0, and 1, 2, 3, 4, 5, 6, 7, 8, 9 times we predicted 1. So we predicted 0 and it was actually 0, so we got this one correct. But this was incorrect, correct, correct, incorrect, correct, incorrect, incorrect, correct, and correct. Does anybody know what the accuracy is here?
What, 60% again?
It is 60%. That was interesting, huh? I didn't do that on purpose. So count up the check marks. 1, 2, 3, 4, 5, 6. 6 out of 10, 60%. Let's do the precision. So true positives. When we predicted 1 and it was actually 1. Great. So above this line, yeah, go ahead.
So I'm curious, just to make sure my brain's not going crazy. If we change the threshold and the accuracy is the same, does that suggest that the precision and recall are going to be the same?
That's a good question. I mean, I might have picked a bad data set example. True positive, true positive, true positive. So now we have 3, 4, 5 over our 5 over our true positive over 5 plus our false positives. 1, 2, 3, 4. So 5 over 9, which I don't think is going to be the same, right?
It's just a little under 60%.
Yeah. Sorry.
It would be, I mean, that's 55.5, I believe.
55.5, yeah. We'll call that 56%.
So not exact. Okay.
Not the same. So
Okay.
your accuracy can stay the same. Our precision went down a little bit. Not a lot here. Our recall, which is going to be, we already did our false positives. Now we just need our false negative, which is when we predicted it was 0 is actually 1. We don't have any. So what's our recall?
Uno. Is it 100%? 1?
1. That's it. 100%. So when we decrease our threshold, our recall goes up. Let's see, trying to think of what color to begin. When we, let me see that. Oh yeah, I think you can. Decrease our threshold. Recall increases. Okay. All right, let's move it to 0.9. And then we'll do the breakout notebook, and then we'll take a break. Perfect. All right, so let's move our, let's erase this, threshold. So let's move our threshold again. And notice we're not changing the model here. We have the same model probabilities. We're just changing this is something called the decision boundary. We're changing where our decision boundary is. So everything below this is 0, and everything above this is 1. So 0.9. So every 0.9 and greater is 1. Less than 0.9 is 0. So let's look at our output here. So we have 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6, 7, 8, 9, and 1 time we predicted 1. So in this case, 0, 0, we were correct, we were correct, we were incorrect, we were incorrect, we were correct, we were incorrect, we were correct, we were correct, we were incorrect, and we were correct. What is our accuracy?
It's still 60%.
It's still 60%. Okay, I did not do that on purpose, and I want to show you guys that the accuracy can change. So just for fun, like if we moved this threshold up 1, and we moved the threshold to, 0.8, well, these two are going to cancel each other out, I think. And that's
0.7? Or is that?
7, yeah. And that was 0. It's going to be incorrect. Yeah, sure. Wait. Sorry, I just made a weird data set here. So if we moved it to 0.7, then these predictions would actually change to 1, 1, 1, 1. This would be correct. This would be correct. This would be incorrect, incorrect. So that would change it to 1, 2, 1, 2, 3, 0.45. So that would change the accuracy to 50% at 0.8. So if we're at 0.8, our accuracy is actually 50%. So, or 0.7, I'm sorry. So your accuracy can change. I just chose some weird numbers on accident that made that not happen. I should have baked data for this so that doesn't occur. But going back to this one, back to the 90% threshold here. What is our precision? Let's look at precision. So we want to know true positives. When we predicted 1 and it was actually 1, we only have 1 true positive in this data set. We only predicted one time, so 1 over 1 plus, 1 over 1 plus. Let's look at our false positives. When we predicted 1 and it was 0, we don't have any of those, so what's our precision? Sorry.
1.
Precision.
100%.
100%, absolutely. Equals 1, which equals 100%. And recall is when we predicted 0, but it was actually 1 for our false negatives. And we have 1, 2, 3, 4. So 4 of these equals 1 over 5, which is 20%. So 20%. So when we increase our threshold, our precision increases. So when we increase our threshold, our precision increases. When we decrease our threshold, our recall decreases. Okay, hopefully that was helpful to you guys and kind of grounded that a bit. Let's switch. Let's look at the breakout. Oh, which I don't think I've dropped yet, so. Let me drop that in the Slack channel. Let's look at thresholds, and let me just move this other one over. Let's look at thresholds. So here's a breakout, thresholds, and the receiver operator curve. We're just going to do thresholds for now. We'll come back to the receiver operator curve. So what you guys are going to do is implement a threshold called predicted labels default that converts probabilities to binary predictions based on a static value. So here we have some true labels, and here we have some probabilities. And what I want you guys to do is implement a threshold function. So just implement a threshold. So implement a threshold of 0.5 and predict 1 when it's greater than 0.5 from these predicted probabilities, and predict 0 when it's less than 0.5. If you call it predicted labels default, so if you say, put this predicted labels default here, then you can just use it in this precision score and recall score. And I want you guys to print the precision and recall at 0.5. And then adjust to 0.3 and notice the difference. If you guys want, you can continue to play around with it to see what the trade-off is between precision and recall on this. So let's spend maybe like 5-6 minutes on this. Okay. A few more seconds. What did you guys have here? how did you guys take those predicted probabilities and convert them to 1 or 0 based on the threshold being 0.5? We can do this should work, I think, a NumPy, we call NumPy. We can do np.where. We're going to take in predicted probabilities. Predicted probabilities is a NumPy array of probabilities here. And we're going to say if it's greater than or equal to 0.5, then it's 1. Otherwise, it's 0. And what this is going to do is, I have to actually import everything here first. All right, so what this is going to do is, I want to look at that predicted labels default. It takes these probabilities, and if it's 0.7, it makes it a 1 because that's greater than or equal to 0.5. If it's a 0.3, it makes it a 0 because that is less than or equal to 0.5. 0.6 becomes a 1. 0.4 becomes a 0, etc. So we can map those. And then we can compare these 1s and 0s here to the actual true labels, the real outcome. So in this case, we predicted 1, but we can see it was actually 0. We predicted 0, but we can see it was actually 1. We predicted 0, and it was 0. So we're going to pass those values, these true labels, and the predicted labels that we generated to this recall score, which is just an sklearn metric. So we're going to import sklearn and that precision score, that recall score, and pass our true labels and our predicted labels. And this is the same way that your model works when you pass your model values. Okay, does this make sense? Kind of? Okay. If we wanted to change it to 3, here, this is very easy. So in this other bit here, it said, hey, change it to 0.3 and let's see the difference. So all we do is we change predicted probabilities to 0.3, and I'm just going to copy and paste this because I'm lazy. And all the names are the same, so this should work just fine. And now, oh, look, our precision and our recall changed. So before we had a precision and recall of 0.4, they were both 0.4. And now our precision is 0.375 and our recall is 0.6. So we decreased our threshold and our recall went up. Okay. Trying to think if we should so let's summarize this and then let's see if I can get you guys out a little early today. Let's do the rock curve because that's only a couple of slides, and then we'll take a break and the second half of that breakout at the same time. All right, that's the plan. Okay, so to summarize thresholds, to summarize thresholds here, they're adjustable parameter. It can be tuned, and it's the trade-off between precision and recall. So by default, if you do nothing and you just get your output probabilities from your model, you may say, well, my model gives me 1s and 0s. It's using a default threshold of 0.5. You can change that. So you can get the probabilities and you can change the threshold. What you do when you change the threshold is you're either prioritizing precision or you're prioritizing recall as you adjust that. Now that we understand that we can get different performance metrics at each threshold, your next natural question might be, well, what if we just evaluate the model at every threshold? So on our whiteboard behind us, we did, the model, the accuracy at 0.1, we did the accuracy at 0.5, we did the accuracy at 0.9. What if we just took that to the extreme and did the accuracy at 0.1, 0.2, 0.3, 0.4, 0.5, and then plotted that on a chart? And then what if we took the area under that? So this is the receiver operator curve, the ROC curve. It's a graphical representation of the model's performance across these different thresholds. And I was talking about accuracy before, but what the receiver operator curve actually measures is the true positive rate against the false positive rate. So we know that there's a trade-off between precision and recall. And so the receiver operator curve enables us to map that trade-off as we increase the threshold or decrease the threshold. So our true positive rate is also known as sensitivity or recall, measures the proportion of true positives, positive predictions among all positive instances. So you guys are familiar with recall. So true positive rate, TPR, recall, same thing. The false positive rate, the FPR, measures the proportion of false positive predictions among all actual negative instances. And then the threshold is the value that separates these. So these are the axes that run along that ROC curve, the false positive rate and the true positive rate. When we look at the ROC curve, when we look at this line on the ROC curve, this blue line here, how should we interpret this? Like, what's good? What's bad? What's this yellow line that runs through the middle here on the ROC curve? Well, that yellow line that runs through the middle is actually random. So if this dotted line that runs through the middle is random. So if we just chose at random, 50% of the time we chose one, the other 50% of the time we chose the other, that's what that would look like. So any lines close to that are quite poor. So this orange line here is quite poor. The green line here is a little better, and then the blue line is very, very good. If it went straight up to 1 and then straight over, that would be a perfect classifier. If it was a L there, that's quite unrealistic. It would be performing perfectly at every threshold. So the ROC curve helps us generalize the model's performance as it varies across these different threshold settings. A curve that, I just said this, a curve that hugs the upper left corner of the plot indicates better performance with higher true positive rates and false positive rates across these different thresholds. So this is how you would read and interpret the ROC curve. You're only going to have curves, by the way, above that random. You're not going to have curves that are below that random line. So the ROC curve is a very useful tool that we can use to evaluate the performance of our binary classification models across these thresholds. So it's a statistic it's a metric that'll allow us to evaluate the difference, the trade-off between these positive and negative instances across these thresholds. So it's threshold agnostic metric, which is a really big benefit. Every other metric that we've looked at depends on the threshold. Precision changes with the threshold. Recall changes with the threshold. Accuracy can change with the threshold. The ROC curve is a threshold agnostic metric. So we have a breakout here, and I want you guys to spend just a couple minutes on the breakout. It's that same notebook here. And play with this receiver operator curve. So we have some fake data from sklearn. We just make some fake data. We split it into training and test sets, and we train a logistic regression model on the training data. We have some probabilities, And we want to compute a rock curve in an area under the curve AUC using matplotlib. So here we have some probs. So we're going to generate some fake data. We're going to split into xtrain, xtest, ytrain, ytest. We're going to create a logistic regression model. And then we're going to predict probabilities on the test set. And we're going to compute, oh, maybe we do this here. We're going to compute the rock curve. So we do actually have the rock curve here. So here's our rock curve. Here's the receiver operator curve. And we can actually get a value associated with this. Did we talk about AUC next? Yeah. So we can actually get collapse all these values into one metric by taking the area under this curve, which is known as the AUC, to actually quantify one value that summarizes the performance of all of these over these thresholds. So what you guys are going to do is compute the rock and AUC. Actually, at least just do the rock for now, just the rock curve, and plot the rock using matplotlib and compare these models. So here, use this example, you can use this same example and structure from above and spend 5 minutes trying to build the rock curve area for the positive class here, given these probabilities and these true labels. So we're generating more random data. So just want to give you guys a chance to practice applying that. Okay. I don't think we're going to walk through that because we have it's the same example up here, just a chance for you guys to apply that. Let's go ahead and take just a short break because we're an hour in here. So let's take a 10-minute break. Let's come back at 7:15, and then we'll talk about AUC, and then we'll have the precision recall curve after that. So 7:15 here. All right. Let's do AUC. So area under the curve, or the AUC, is a measurement that represents the performance across all of those possible thresholds for the model. So if we take, looking at this, remember we said if it's runs all the way up to the top here and then runs over, that's theoretically a perfect model. I'd be very concerned if you had a perfect model, and so that's not what we see in reality. But if we took the area under this curve, which looks like an L-shaped line now, that area would be 1. And if we took the area under, remember I said models never go below this random line here when we're measuring, it only goes up to that random line, it's 0.5. So this value actually ranges from 0.5 to 1. So the area under the curve is going to be somewhere between 0.5 and 1. I know I have 0 to 1. It's theoretically 0, but the area under the curve will really be between 0.5 and 1 as we look at the rock curve, the area under the rock curve. So values closer to 1 indicate that the model is performing better, and values closer to 0.5 suggests that the model performs no better than random guessing. So this is a metric that you want to maximize as opposed to minimize. So if we had, sorry, I keep jumping around a bunch here, but this right here, let me just draw on this. For example, the area under this curve here would look like all of this. We're measuring the area under the curve. So this area. And as you math enthusiasts know, we can use calculus to measure the area under that curve. So the AUC is a singular scalar metric, and it quantifies the performance of a binary classification model over all possible thresholds. So we can use it to measure like the area under that rock curve, for example. Maybe I have this in advantages. Okay, so we talked about interpretation. The advantage, really big advantage here of the AUC is that it's a threshold independent metric. So we don't have to set a threshold. We looked at that at precision and recall and accuracy and how those values change depending on the threshold that you set. This is a threshold agnostic, threshold independent metric. So it evaluates the model's performance with no need to choose this particular threshold. That's really the biggest advantage of the AUC metric, and it's robust to class imbalance since it's threshold independent and doesn't necessarily require balanced data sets to provide meaningful insights. The limitation here on AUC is that it doesn't, this is a big one, this is important. I think people miss this sometimes. AUC does not provide any insight into how the model performs at a particular threshold. And so when we put a model into production, we actually have to serve a prediction. So we have to choose a threshold because we have to, if somebody wants you to predict the likelihood of an event occurring, the likelihood of fraud, the likelihood of spam for a particular email, you actually have to be able to tell them, yes, this is spam, or yes, this is fraud. You have to serve a prediction at the end of the day. So we do have to choose a threshold for models that have probabilities. So AUC is great. It provides a lot of insight. It provides a lot of analysis. It doesn't help when we're actually putting these models. We need to actually evaluate the model at a particular threshold. And we actually need to serve a prediction and implement that and measure that. So AUC limitation, biggest limitation is doesn't evaluate at a particular threshold. Same thing as it's opposite of its advantage. So it's a very widely used metric for assessing the performance of a model, regardless of the threshold that you set. And it's a pretty comprehensive summary for looking at all possible threshold settings. Oh, I was close to the break. I had it here. Okay, now let's look at the precision recall curve, which is very similar idea to the ROC curve that we're looking at. One question you might ask is, well, ROC curve had recall on it, and then we had this other rate that we were measuring. Why wouldn't we just measure precision versus recall? And we can do that. And there's a lot of good reasons to do the precision recall curve instead. So here we have the precision recall curve. Notice this chart is going the other direction here. So the other one was going left to right. This one is going kind of right to left here. We have precision on the left axis and recall on the bottom. And the precision recall curve is a graphical representation of the trade-off between precision and recall across these various thresholds. So we kind of played with this ourselves. We put 0.9 up there, we put 0.1 up there, and we saw that when we increased our threshold, precision increases and precision eventually gets to 1. So as we increase our threshold, we see that precision eventually gets to 1, and it's actually 1 for this entire time here and for this data set. And when we decrease our threshold, then recall increases, and recall actually eventually gets to 1. So it's 1 down here in the corner. And then here we have the plot of the precision value, the recall value versus the precision value for all of these different thresholds, for every threshold. Okay. So similar to, let me pause here. Any questions on the precision recall curve thus far? Okay, great. So similar to the ROC curve, we can also take the area under the curve, the AUC. So we can also take the AUC over here. The AUC would be the area under this curve, so the area up to here, and we can see that it's 0.930. And then the area here, we can see that this is 0.591. So similar to the ROC curve, we can take the area under the precision recall curve, and that will give us one metric that represents the performance of the model across all thresholds. So one metric that represents the performance of the model across all these threshold settings. Of course, it's a metric that we want to maximize. A higher AUC PR value indicates a better model performance, and a lower one is a worse performance. So is true positive rate the same as recall? So here we have the recall, and here we have the true positive rate. Are these things the same? The answer is yes. So the true positive rate and recall are the same. They both refer to the proportion of true positive predictions among all positive predictions. What about, let's look at the other dimension here. Well, what about false? And also, I just want to note that the recall here is on the bottom, and the recall here is on the y-axis. So this one's up. On one chart, the recall is on the x-axis. On the other chart, the recall is on the y-axis. What about false positive rate and precision? Are these essentially just the same charts? Is the false positive rate the same thing as precision? And the answer is no. So the false positive rate is calculated with this formula, which precision is calculated with this formula, which we're very familiar with now, true positives over true positives plus false positives. The false positive rate, I have to plug in my computer, so give me a second while I should have done that earlier on the break. The false positive rate is the false positives over the false positives plus the true positives. True negatives, I apologize. So I guess what I'm just trying to emphasize here is that the recall and the true positive rate are the same thing, but the false positive rate and the precision are different things. So precision versus recall. When do we use which one? Or precision recall curve, the PR curve, versus the ROC curve. When do we use each one? So over here on the right, we have the receiver operator characteristic, ROC curve, and over here we have the precision recall curve. So the precision recall curve is one that will serve you better when you have class imbalance. So if you have a lot of class imbalance in your data, the precision recall curve is going to represent that trade-off a little better than the ROC curve. And the ROC curve is typically used when there's better class balance there. But really, there's no particular downside to mapping out both and applying both. Did I hear a question? No? Okay. All right, excellent. Let's do one more breakout activity, and then we're going to do model calibration, and then that's it for today. Oop. All right, let's pop over to this AUC and precision recall curve. You go ahead and spend 5 minutes walking through calculating the AOC using the ROC AUC function for this logistic regression example here. So down here, I want you to calculate the AUC for the random predictions example. And then for the precision recall, try plotting a precision recall curve for the two examples above. And this is maybe what it looks like or not. Spend we'll just do 5 minutes till 35 here. Okay. Does anybody have code they want to share for calculating the AUC here? AUC. See. I thought it would autocomplete for me. It's not. Let's go look at this AUC from sklearn and see what it takes. AUC, sklearn. Looks like it takes in X and Y. So once here's an example. We have Y here, we had pred. Rock curve, oh, it looks like from rock curve, metrics.rock curve, we can just call metrics.AUC, true positive rate, false positive rate. There we go. Rock curve, we don't need the metrics. Yeah, just rock curve. Oh, from metrics. Let's get in metrics. AUC, that was right before. Equals AUC. And it looks like we're just passing the false positive rate and the true positive rate, which we're grabbing here. Oh. There we go. So we should be able to just print this rock AUC. Oh, predicted random probabilities between 0 and 1. We are missing that. One moment. Is this something from above? Not sure. Maybe I have this in here twice. Move this up onto this curve here. There we go. There. So now we have the rock curve of 0.92, and I'm sure where this one was. Okay, it does need true ripples. Let's see if we can put some props here. Okay, we'll leave this one for now. So we should be able to get the rock AUC here. And we do, yeah, so 0.92, which we saw in the chart. And then let's do the precision recall curve. Let's see if we can do the This will probably, does somebody have code they want to share? This will take a minute. Okay, I'll get the answer to this one and then share this afterwards, and then you guys can compare and contrast the precision recall curve. I think those are just the same ones that I have on the slide, so it's not going to really be any surprise there. Let's dive into our last topic here, model calibration. How does that sound? All right. So now that we talked about the predicted probabilities that are output by machine learning models, we can start to talk about an important piece, which is interpretation. The interpretation that humans have when they're looking at the probabilities associated with this. So algorithms that produce these probabilities, we interpret that as the model's confidence in its prediction. Hold on to that thought for just a moment. I think the piece I want to get to is here. Well, we interpret these as I think I want to get to this piece. We interpret this as the probability associated with the model's prediction. So if I tell you that the probability is 80%, you're going to expect that 80% of the time that outcome occurs, and that 20% of the time it does not occur. And if I tell you that the probability of the coin toss outcome is 50%, you're going to expect that 50% of the time that occurs and 50% of the time it does not occur. However, some of these models, when we output those probabilities, that does not match reality. When you look at the distribution of probabilities that come from the model, oftentimes you'll see that values close to 0.9 and values close to 0.1 are underrepresented because the model is kind of has a reward policy for not producing overly confident predictions. So what you'll actually see is a lot of probabilities kind of clustered around that 0.3 to 0.7 range, and less probabilities on those outer boundaries. And that doesn't always represent reality, is in terms of how often we see these instances occurring. So it's just fine. It doesn't actually change any outcome unless you are serving these probabilities to people. So if you're giving your probability or your outcome to a machine, if we have thresholds and we're just saying 1, 0, this doesn't really matter. Where this does matter, and I have seen this twice now in production models that we have built and served for customers across 2 different companies. And where it does matter is when you're giving these probabilities to an actual individual and you're telling them, look, here's the probability that this outcome is going to occur on this person. This is the probability that this is actually going to happen. The probability this person's going to cancel their policy. The probability that we're going to win this case. If you tell them the probability is 0.75, and then out of every 4 cases that they see, they're going to want to see that happens 3 times, 3 out of 4 times. You're going to want those probabilities to match their reality of how often they see that outcome actually occur. So there's a lot of preamble. What we can do is apply model calibration. So model calibration can adjust our predicted probabilities to fit alignment with the outcome occurring. So it will move and shift the probabilities so that 20% of the time, if we're predicting 0.2, then we're predicting that event to occur 20% of the time. If we're predicting 0.4, we're predicting that event to occur 40% of the time. If we're predicting 0.6, we're predicting that event to occur 60% of the time. Model calibration does not change the order. So if we have, I'm trying to think of a better way to draw this than this. So over here on the right is the diagram. This orange line is the distribution of the model's prediction and outcomes, and the blue line is where we want to get to. So you want to move that distribution so it aligns with the blue line, so that it says 20% of the time we're predicting this likelihood will occur at 0.2. 40% of the time we're predicting this likelihood will occur. 90% of the time we're predicting this likelihood at 0.9. We're predicting 9 out of 10 of the records that this likelihood will occur. That's obviously not how this model is working now. There's kind of some underrepresentation here. So when we do model calibration, if we have these predicted probabilities, we have like 0.2. For some reason, we have this cluster of like 0.2. This is just what our model did. And then we've got nothing, nothing, nothing. And then we have 0.5. And then we've got nothing, 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 and 0.9. Well, let me put a 0.8 in here. It'd be easier to explain something. 0.8, 0.9, and 0.9. What model calibration is going to do is it's just going to smooth those out. And so it's not going to change the order of your probability predictions at all. So it doesn't violate anything. So maybe this will be like 0.2, 0.3 for this guy. And maybe this guy's like 0.4 now. And this is 0.5. And you can imagine this was like 0.20, 0.21, 0.22, so you can kind of put some ordering there to those. Maybe this 0.8 gets shifted down to 0.6. Maybe this 0.9 gets shifted down to 0.9 here, and then this one remains 0.9. So now we have a more representative distribution of probabilities. Let's look at this next slide, because maybe this will help a different way of viewing this and thinking about this. For example, look at these predicted scores on the right here. We have a lot of times where the model's predicting 0.2, and a lot of times where the model's under predicting here in the middle. And in this case, it's over predicting on this 0.8 bucket. And then, like I said, interestingly enough, it's not predicting anything between 0.2 and 1. And it's not predicting anything between 0.8 and 1. So our model is afraid of being overconfident, saying, yep, for sure, this will definitely not occur. It's kind of hedging its bets if you look at those distribution of probabilities. It's being conservative. The model is being conservative. But to a stakeholder, just a normal human interpreting things, they want to see a 0.9 that represents, 9 times out of 10 that is going to happen. And so what we can do is, with the outcome and I don't know exactly where this line would fall, but the outcome that we want is to see a uniform distribution. If you guys remember statistics class, that's why I had these slides in here earlier. Uniform probability that the outcome will occur at each threshold. So we want to smooth out that probability distribution. And we can do that this is called calibration. And this is something you can apply to your model afterwards. It doesn't actually really change the performance of your model, or like what your model is doing, or how it's making its decisions, or the outcome. It's simply to make it more interpretable to us as humans. That's how I would describe it. It doesn't change the order of recommendations. So if one person was 0.91 and somebody was 0.90, the 0.91 will always have that higher value. So it's not changing the order. It's not really changing anything your model does, other than ensuring that when we serve a prediction of 70%, that the actual occurrence rate of that event is close to 70%. So it's something that we enforce on the model in order to make these predictions interpretable and feel right to humans, basically. So in a perfectly calibrated model, the average predicted probability over all instances is equal to the observed frequency of those positive outcomes. You can just, there are techniques that you can use to apply this calibration. We can apply isotonic regression, other specialized calibration algorithms, plot scaling, and this will just map those raw scores to the calibrated probabilities. So this is just a transformation. You could think of it as a transformation that we tack on after the model output. So if we have a model pipeline, we have the model prediction, and then we have the transformation. We can tack that on after. So we can apply calibration plots. We can make calibration plots, and we can plot raw models, so logistic regression versus random forest, and see which one is more natively calibrated. We can evaluate how well they are outputting this distribution relative to kind of that perfect calibration. And like I said, we can actually enforce that. So the model calibration ensures that these predicted outputs, they're reliable estimates of true real-world probabilities. If we say 0.5, means half the time it happens, half the time it doesn't. It's an important aspect of model evaluation when you're serving this to an actual human being, and somebody's interpreting this probability and using it in their workflow. And I do have a notebook for this. Let me grab that real quick. So I don't think I put that in the Slack. Let me drop that in the Slack. Oh, sorry. Christelle, I just saw your message. Yes, I will respond on here with that. I'll give you guys a link for submission for the assignment, and I'll give you guys a link for the slides and other content. Okay. All right, I just dropped a model calibration exercise. You guys want to go through that in the Slack channel. Other than that, I'm going to end the stream and see if you guys have any questions.